Dear students, just to go through the concepts, whatever you have studied in the previous class, we'll start the session within 5 minutes once everyone joins. Good morning, students.
Good morning.
Good morning. Since the attendance is low, maybe due to some lack in information, so we'll not discuss the general lecture in this session. Rather, I'll be giving questions to you, so you try to solve those questions like a practice session. Okay. So try to solve this first question. The major product are in the following sequence of reactions: CH triple bond CH converting into P whenever it react with LiNH2 in the presence of ether. Second set of reagents, CH3.
Sir, screen is not shared.
Just a second. Okay. CH3 CHBr. CH3 taken twice. CH3 gives your product P. Product P react with a HgSO4 in the presence of H2SO4 followed by NaBH4 gives product Q. H plus upon heating gives R. Find the major product R. CH triple bond CH acetylene treated with the lithium LiNH2, Li plus NH2 minus. Like NaNH2, it is also a strong base, LiNH2. Followed by CH3, CHBr, CH3 taken twice. This will be giving product P. Product P, HgSO4, H2SO4 gives product in the presence of NaBH4 gives product Q. Q treated with H plus in the presence of heating gives product R. What is the product R? Try to solve this question, students, all of you. All of you try to solve this question. So if you try to solve this question, what happens in the first case? CH triple bond CH treated with LiNH2 in the presence of ether.
NH2 picks up the proton and generating sp.
Yes, very good. So first step is very simple solution. If you go with that solution, CH triple bond CH treated with LiNH2. LiNH2 is a strong base, so it will form respective HCl triple bond C minus Li plus. Along with that, ammonia is going to be released out. This is now going to be treated with an alkyl halide CH3, CHBr, CH3, CH3. This was the alkyl halide given to you. But if you look at this alkyl halide, what type of alkyl halide it is?
2 degree.
2 degree alkyl halide. 2 degree alkyl halide can undergo 2 degree alkyl halide can undergo SN, like if there's a competition always, SN1, SN2, E1, E2. These are the 4 cases. E2, can I do E2? Look at this. Not a very strong
Yes, sir.
base. E2, I cannot. Not a very strong base, right?
Yes, sir.
E2, we have to think only in the presence of alcoholic KOH, tertiary butoxide, methoxides, but it is not a very strong base, so I can eliminate E2. SN2, I can eliminate because with respect to the carbon on the beta carbon, this is alpha, this is beta. On the beta, we have branching, so that is why I have eliminated SN2. E1, I can eliminate because temperature they have not made. Temperature condition they have not mentioned, so I can eliminate E1 also. So only logically I have to proceed with only SN1. SN1 means I have CH3, CHBr, CH3, CH3 because I cannot do SN2, I cannot do E1, I cannot do E2. So only SN1 I have to do. Form a carbocation CH3, CH plus, CH3. Slow ionization to form a carbocation is SN1, RDS. And now what happens? Rearrangements possible. So 1, 2 hydrate shift. If you do the 1, 2 hydrate shift, what is going to happen? You will generate CH3, CH2, C. Now the carbon will be having a positive charge, CCH3, CH3, CCH3, CCH3 with a positive charge. Now the nucleophile will attack. What is the nucleophile? HC triple bond C minus. This will be acting as a nucleophile, attack the electrophilic carbon, generating CH3, CH2, C, CH3, C, CH3, C triple bond CH. This is nothing but your product P. This is nothing but your product P. Everyone got this or not? CH3, CHBr, CH3, CH3. Because first step is formation of the respective nucleophile, CH triple bond CH in the presence of a strong base. It will be undergoing the base will pick up the proton, form the respective nucleophile. That nucleophile will attack the electrophilic carbon, but SN2, SN1 only is going to happen, not SN2 because of bulky groups on the beta carbon. E1, E2 not possible, E2 not possible because there is no strong base. E1 not possible because temperature condition not mentioned. So only logically we have to follow the SN1. Generated a carbocation, done the rearrangement, and then the nucleophilic attack. So this was your compound P. Compound P, all of you got it, I think. Compound P treated with a H plus in the presence of heating. Compound P treated with HGSO4, H2SO4.
Addition of
Compound,
water.
yes. Compound P, if you go with CH3, CH2, CH2, C, CH3, C, CH3, C triple bond CH. Hg, whenever you look at the HgSO4, H2SO4 alkyne, you have to simply add water according to Markovnikov rule. CH3, CH2, CCH3, CCH3. This carbon should be adding the OH and the other carbon will be adding the hydrogen. Now you can respectively write the tautomerase structure. If you can write the tautomerase structure, you will get CH3, CH2, CCH3, CCH3, C double bond O, CH3. This is nothing but your ketone. Addition of water you have done to terminal alkyne. And according to Markovnikov rule, you have to do. Ultimately, you got the respective ketone. That ketone, can I do the tautomerization? That ketone, the ketone is obtained upon tautomerization. That ketone I am now treating with NaBH4. NaBH4 can reduce ketones or not. NaBH4 will reduce 4 functional groups: aldehydes, ketones, acid halides, imines. So respective oxygen containing functional group will be converted to respective primary alcoholic group or alcoholic group. So C double bond will be converted to CHOH. You will generate CH3, CH2, CCH3, CCH3, CHOH, CH3. This is nothing but your compound Q. Everyone got this or not? CH3, CH2, CCH3, CCH3, CHOH, CH3. This is nothing but your compound Q. How did I get this compound? I have added water to alkyne system. After addition of water to alkyne system, I have done the tautomerization, get the ketone. That ketone I have reduced with NaBH4, got the respective alcohol. This is your compound Q. Compound Q treated with the H plus upon heating. What type of reaction is last one? Compound Q treated with acidic dehydration, dehydration of alcohol. Yes or no? Lone pair of electrons on oxygen, they will attack the proton, generating CH3. In the dehydration of alcohol, you will get what? First step is the protonation of alcohol. Second step is the loss of H2O to form the carbocation. H2O is going to be lost and you will generate a carbocation. And third step is the generating more stable carbocation because carbocation is obtained, rearrangements are possible. I can do the rearrangement. What rearrangement I can do? Ethyl shift, I can methyl shift. But what is going to happen? Methyl shift occurs. 1, 2 methyl shift. There is no hydrogen. If I do the methyl shift, I'll generate what? I'll generate CH3, CH2, C, CH3, C plus, CH, CH3, CH3. After doing the methyl shift, that is rearrangements, whatever possible, finally HSO minus will come and pick up the proton. HSO minus will pick up the proton in such a way such that the alkene formed is going to be the most stable or major alkenes. Will generate CH3, CH2, C, CH3, double bond C, CH3, CH3. This will be the respective R or major product. Everyone got this or not? So sequence of reaction, I have started with a simple acetylene treated with NaNH2 in the presence of ether, then alkyl introduced, then addition of water to alkane, then reduction, and then dehydration. Like I can include every type of question in the same reaction sequence. You may not be having this much lengthier questions, but a part of such questions can be asked. Okay, a part of such type of questions can be asked. Is that clear, students?
Yes, sir.
Yes, right. So next question. Yes, try to solve this question. I have given a compound to you in this manner. First treated with tertiary butoxide, then treated with concentrated H2S4 upon heating. What is the major product? Try to think on this question for a minute at least. After that, we'll solve. And here we have chlorine. Okay. Sorry, here we have chlorine. Is the question noted? So if it is noted, I'll write the next question. Meanwhile, you can try.
Yes, sir.
Yes, right. Very good. All of you try that question. Next question, a carbonyl compound P which gives positive iodoform test. Undergoes reaction with CH3-MgBr followed by dehydration to give Q. Ozonolysis of Q leads to R, which upon treatment with OH minus on heating gives S. That is, this is a sequence of reaction P CH3-MgBr, first one, first set of reagent, second set H3O plus, third H2S4 upon heating gives your respect to Q, O3 ZnH2O gives R, OH minus heating uses. What are P, Q and R? That's the question. Ultimate question will be what is P, what is Q, what is R? So let us go with the previous question first. Anyone solve this question? What happens the first step?
Tertiary butoxide will form an alkene.
Tertiary
By
butoxide
picking up
will try to pick up the proton and form a respective alkene. So what type of alkene is that going to be?
Hoffman alkene.
Hoffman alkene, or like where you will get the double bond. So here we have a carbon to which hydrogen is connected. On this particular carbon, only one possibility if you look carefully. There is no Hoffman and ZF. This is the alpha carbon to which fluorine is connected. This is a beta carbon, right? There is no another beta carbon. So obviously tertiary butoxide has to go and pick up this proton, even though it experiences slightly repulsions. It will form an alkene, that is a double bond is going to be formed, which will be in conjugation with respect to this C double bond O. So this will be obtained whenever tertiary butoxide comes and pick up the proton, forming the elimination, that is E2 elimination occurred. E2 occurred and you get this one. Now you are treating this with H2S4 upon heating. So it is not a simple C double bond or C double bond C. It is a conjugated system. The carbon-carbon double bond is in conjugation with C double bond O. So can I say whenever this is treated with H2SO4, like the H plus from H2S4 is going to be attacked by lone pair of electrons on oxygen. Why? So you may ask a question, sir, why can't the double bond will attack the H plus? If you look carefully, the pi electron density can move here, and the C double bond of pi electron density can move in this direction, developing more electron density on oxygen, which is more stable or not? Yes or no? From the resonating structure also, we are getting negative charge on oxygen, which will be more stable. So oxygen being electron rich in nature, and it also has lone pair of electron that can be easily attacking the H plus ion. That is more favorable attack, not the C double bond C of H plus directly attacking. So in that case, what is going to happen? You will generate a compound in this manner. So we have a benzene ring substituted with the isopropyl group as well as CH2, C double bond O, oxygen has only one lone pair and OH bond is formed and a positive charge, and you have C double bond systems. Now I'll add the respective resonating structure for that. So we have this structure. What is the structure, students? Can I write the pi electron density movement here and C double bond electron density movement because the electrophilicity have increased? So because of that resonating structure, I'll be having this structure. Now what will happen? Up to now, everyone can do because there is no issue so far. Tertiary butoxide means you have to think of elimination only. I have done the elimination, formed an alkene. That alkene, the C double bond C is in resonance with C double bond O. So lone pair of electrons on oxygen have attacked H plus because there they have more electron density. generated the respective compound in this manner. So where I have written the resonating structure, form a carbocation. Now what I can do, and I have a double bond here as well. Now can I think of any reaction? Anyone got any reaction from this step? What Faizan? What you have done here?
I'm stuck here only.
So here what happens is, with respect to benzene ring, you will be having the electrophilic substitution reaction happening. Okay, so that they will never mention. With respect to benzene ring, on the benzene ring we have a substituent also. You look carefully. What type of substituent it is? Isopropyl group. That is electron donating or electron withdrawing group?
Electron donating group.
Electron donating group, and we have the alpha hydrogen also, because with respect to the benzene, on the alpha carbon we have hydrogens also, so it is plus H. It is electron donating group, and the electron donation is happening through hyperconjugative effect, so it is ortho para directing. If it donates on the ortho position, whatever the electrophile substituting here, that will experience repulsions, so the para position is going to be attacked. Okay, so that is going to happen now. So the pi electron density is now going to be attacking this particular carbon, leading to the formation of this ring. So you have double bond here, these two positions, and you have a positive charge here because the electron density moved away from that carbon. This is 1, 2, 3, 4 numbering I have given, and this was 5 and 6. So this was sixth carbon as it is, and fifth carbon is now connected with which carbon? Fourth carbon. Fourth carbon is now connected with third carbon, third to second, second to first, and where the substituents are, between 2 and 3 we have a double bond. On the second you have OH group. Yes or no? The fourth carbon, which has a positive charge, that was nullified because the pi electron is attacked. Fifth carbon is now going to have no charge because it has used the same electron density to attack. But sixth carbon, which has seen a loss in electron density, that will get a positive charge. But if you look at the initial species, it is aromatic in nature, but this is just resonance stabilized. So to regain back the resonating nature, what happens? HS24 minus, which was present in the reaction mixture, that will try to pick up this proton. CH electron density comes into, and you will have this product. Yes or no? Once you get this product, and if you look at the enol system, that enol system can be again tautomerized or not? This can be tautomerized, and that can be tautomerized to give the respective keto form. You have C double bond over here. This was the respective major product. Got this or not, students?
Yes, sir.
Okay, so these are some miscellaneous questions. You don't need to panic and all. So I'm just relating every type of question so that it's not like from one chapter or the other chapter. Intermixing, how we can have different types of question, how we can solve all the questions, how we can think of them like that. And the first step and second step, they are going to be fine, but the electrophilic substitution, no one is going to mention you. If they have given constant HNO3 in the presence of H2S4, you can guess it. Just they were talking about nitration, electrophilic substitution. Free radicals, alkylation, acylation, halogenation, all those, if I use the reagents, you can do it. But in case if the reagent is not given to you, in case the carbocation has been generated on the substituted substitution of the particular benzene ring, then you have to again think of electrophilic substitution only. Okay, right, very good. So try to solve this question. A carbonyl compound P, look at this, you don't need to write all this, just this sequence, reaction sequence. P treated with CH3 MgBr, H3O plus, acidic hydrolysis, then H2S4 upon heating generates Q. O3 in the presence of ZnH2O, reactive ozonolysis generates R. R, OH minus upon heating generates S. P to Q, Q to R, R to S. Try to think of, all of you just think on this particular question. So let us solve this question. P is a compound which is upon treatment with CH3 MgBr H3O plus gives H2S4 upon heating, right? And the first question, if you understand this particular question, and the first question in this perspective is like the structure of the carbonyl compound P is. What is P that you have to find out? If you read the question, structure of P is. Okay, this was the first question which has been given to you. The structure of P is P treated with a CH3 MgBr, then acidic hydrolysis, then H2S4 upon heating generates Q. So which is the structure of P? And if you choose the structure of P correctly, so with respect to all these reagents, okay, undergoes reaction with CH3 MgBr followed by dehydration to give an olefin Q. Ozonals of Q leads to R, which upon treatment with OH minus upon heating means what? Leads to R, which upon treatment with OH minus upon heating. What is that reaction? You have done the ozonolysis and you are getting R. R will be dicarbonyl generally. Yes or no? If you do ozonolysis, yeah, dicarbonyl. Here they are talking about intramolecular aldol. Okay, intramolecular aldol. Now let us try to look at the product P. A carbonyl compound P which gives positive iodoform test. Which can give positive iodoform test? Look at the option, set of options. First you have to eliminate. CH3 C double bond O group should be there. CH3 C double bond O. This is present here, option A. CH3 C double bond O, option B also possible. C2H5 C double bond O, will it show positive iodoform test? A carbonyl compound P which gives positive iodoform test for a what is the condition to give iodoform test? We should have CH3 C double bond O group or CH3 CHOH group. Yes or no? These two groups should be present because the CH3 CHOH can be undergoing oxidation to form same CH3 C double bond O. But if you look at the question, like there are a lot of sequence of reactions, right? Starting from P, we have to do some 6 to 7 reaction, then only we'll get S. I cannot do that 6 to 7 reaction for starting from A compound, B compound, C compound, D compound, all. That will be time consuming and waste of time. That is not the way they want you to think. First, they have asked you, like it will be undergoing positive iodoform test. So I can, based on that, I can eliminate option C. Option C I can eliminate. And similarly, option D also I can eliminate. CH3 CH double bond CH C double bond O. Option D also I can eliminate. So among option A and B only, our correct answer should be. So we have to think of any option. Like let us start with option A. Let us start. If it gives every set of reaction whatever we have predicted, then it's fine. If not, we have to think of other option B. So this is your respect to option A. This I am treating with what? CH3 MgBr. CH3 MgBr means what? CH3 minus will be acting as a nucleophile. It will attack the electrophilic carbon. It can act as a base also whenever there is an acidic proton, but in the compound A, whatever they have given, there is no acidic proton. CH3 minus will be acting as a nucleophile, attack the electrophilic carbon, generate this particular compound. Already one methyl is there, one more methyl is added. Now this has been O minus will develop electrostatic force of attraction with MgBr plus. Now we have done the H3O plus, that is H plus in the presence of H2O, acidic hydrolysis. You will generate the respective alcohol. CH3, CH3, COH. Everyone got the respective alcohol, right? This alcohol now treated with a Now treated with what? H2SO4 upon heating. H2SO4 upon heating means H2SO4 upon heating means dehydration.
Protonation of alcohol occur.
Yeah, first step is protonation, then formation of respective carbocation, then elimination to form the alkene CH3 evaporating. Now it will undergo loss of H2O. If it undergoes loss of H2O, it forms what? Positive charge, two methyl groups. From where we can have the, from where we can do the elimination now?
From the two methyl groups.
Okay, from where we can do the elimination, I can do elimination from the two methyl groups. That is the first logic which you can think of. If I can do elimination from the two methyl groups, what is going to happen? I'll be generating a system in this manner. I have carbon-carbon double bond. Here I have one methyl. Yes or no? This is the point or not? Because I cannot remove the proton from this particular, like a beta. This is alpha. This is also beta. This is also beta. This is also beta. These three beta carbons, I have to know. If you have to choose, I cannot pick up proton from here because that will generate alene system. That's not possible. So these two beta carbons you can try to pick up and form respective alkene in this fashion, right? Now what will happen? Now what will happen, students? Think of the question again. P treated with CH3 MgBr. P treated with a CH3 MgBr. P treated with CH3 MgBr. Then you have done the respective hydrolysis. Then you have done the elimination of water, the dehydration to form this type of alkene. This type of alkene, whatever obtained, that can be undergoing then ozonolysis. You have to do the ozonolysis of this reaction or not? I think there was some technical issue. Try to do the ozonolysis of that particular substance. Try to do the ozonolysis of Q. Just a second. Try to do the ozonolysis of Q. If you look at the compound, It was something like this, right, Q? Yes or no? And this was a sequence of reaction P treated with MeMgBr followed by H plus in the presence of H2O followed by H2SO4 upon heating. Q treated with O3 ZnH2O, R treated with OH minus upon heating. So I have given the option P. First option is this one. Option A. Option B is one more substitution placed. C and D, we have seen that C and D do not have CH3 C double bond group, so they will not be undergoing the respective dehydration. So from the compound Q, if I try to do the ozonolysis, if I treat this with O3 in the presence of ZnH2O, before generating compound Q, I get what? This type of product. Yes or no? This type of system is there, where I have a positive charge here and CH3 and CH3, and I have done the elimination. Okay, elimination I have done E1 to form the respective compound in this manner. But if you do the ozonolysis of this particular Q, are you getting a dicarbonyl? Q upon treatment with O3 in the presence of ZnH2O produces R, which should be a dicarbonyl. Is that a dicarbonyl? R is a dicarbonyl compound. R is a dicarbonyl compound. S is intramolecular aldol. S is intramolecular aldol. So that's what they have mentioned in the question as well. But R is a dicarbonyl compound. If I do the ozonolysis of this particular reaction, this bond is going to be broken. I'll get C double bond O. This bond is also going to be broken. I'll get a C double bond O. So what I'm going to do, if I do the ozonolysis, if I treat this with O3 in the presence of ZnH2O, I'll be getting what? I'll get C double bond H benzaldehyde. Along with that, this carbon CO2 I'll get, that is HC double bond H, which can undergo further oxidation, and I'll generate C double bond H plus C double bond H. This dicarbonyl will not undergo intramolecular aldol. If you look at C double bond H, C double bond H, will that undergo intramolecular aldol?
No, sir.
No. So this is wrong. So whatever the product you obtain here Q, that is wrong. So can I say option A is wrong? Can I say option A is wrong? If I proceed with option B also, what extra I have? Let us go with what extra I have. If I proceed with option B also, C and D I have eliminated because they are not undergoing a Iodoform test. A and B have to choose one. I have started with A, end up with this compound, which cannot be forming a dicarbonyl, which will undergo intramolecular aldol. But if I choose with B also, I'll be getting methyl here. That's it. That is the only extra thing in A and B. So I'll be getting methyl here, means here instead of H we have CH3. So that in the set of compounds B also, am I going to get the respective dicarbonyl and intramolecular aldol? Is that possible? It is not possible with A and B also. So how is that? How is that happening then? How is that happening means here what mistake we have done again is, whenever we produce this carbocation, okay, we have directly done what? We have directly done elimination reaction. Okay. This cannot form dicarbonyl, which can undergo intramolecular aldol. So this is wrong. So what reaction you have to think of is this P upon treatment with the CH3 MgBr followed by acidic hydrolysis followed by H2S4 upon heating, I form a carbocation, right? Instead of directly forming the instead of directly doing the elimination and forming the alkene, what reaction you can think of? Anyone can say it?
Resonance of
Yeah, resonance you can do. If I do write the resonating structure, I'll get what? I'll get a positive charge here, double bond, CH3. Yes or no? With resonance, what I can do?
so this will also be wrong. Electrophilic substitution can occur.
Yes, very good. Electrophilic substitution you have to do, not the resonance. Okay, if you do the resonance and do the electrophilic substitution, that will form three-member ring. But if you can think of this pi electron entity attacking this particular carbon, it will form a five-member ring, which is more stable. So electrophilic substitution you have to think of, not the elimination. So you will be forming a respective compound like this. I'll give the numbering 1, 2, 3, 4, 5. So this is first carbon connected to second. And the first carbon attacked the fifth carbon. Fifth carbon has two methyls. Fifth to fourth connection. Fourth and third double bond. Yes or no? And second carbon has a positive charge. And now HS4 minus will come to the scenario and it will try to pick up this proton present on the first carbon, needing to regain back the aromatic nature, generating this particular compound. This is your compound. Yes or no? This will be a respective compound. CH3, CH3. From this particular compound, if I try to do the elimination, like if I do the ozonolysis, I'll be getting a dicarbonyl. Will that dicarbonyl undergo intramolecular aldol or not? We'll check. This is your Q as of now. This Q did with O3 in the presence of ZnH2 dicarbonyl. Q is this particular compound. The five-member ring is obtained here. Two methyls present. This I am reading with the O3 in the presence of ZnH2O. O3 in the presence of ZnH2 is reductive ozonolysis or oxidative ozonolysis?
Reductive ozonolysis.
Reductive ozonolysis means you have to simply give the sigma and pi bond both and substitute C double bond O wherever it is present. C double bond OH, CH3, CH3. C double bond OH, C double bond OH. It is a dicarbonyl or not? It is going to be respective dicarbonyl. In this particular dicarbonyl, this dicarbonyl will undergo intramolecular aldol only. I have given the condition. When the intramolecular aldol is possible, what type of rings should be found?
5 to 6 months.
Yes, only intramolecular aldol is possible only if 5 or 6 member rings are formed. What type of rings are formed here? With respect to C double bond O, here on the alpha carbon we do not have hydrogen. With respect to the C double bond O, this is the alpha carbon. On this alpha carbon also, we have a hydrogen. CH3, CH3 carbon, already 4 bonds are done. There are no alpha hydrogens, so it can't undergo aldol. Can't undergo aldol first of all. We forget about intramolecular aldol and all. It can't undergo aldol because there is no alpha hydrogen. So whatever the product I have chosen, that is whatever the compound I have chosen here, that is wrong. So I have to choose compound B. Compound B, in the compound B and compound A, what do we have the variation? Only this methyl. Yes or no? So wherever you have CH, double bond CH, I have to place methyl. So option B should be correct. Should be correct. And if you look at the correct option, that will form this type of product. Only the variation which you are seeing is wherever you have a double bond, C double bond C, there to this particular carbon you have methyl. That is the extra methyl you have or not?
Yes, sir.
Now you treat this with O3 in the presence of ZnH2O. You get a compound in this manner. C double bond OH, CH3, CH3, C double bond O CH3. Will it undergo intermolecular aldol? With respect to this C double bond O, alpha carbon is there and the alpha hydrogen is there. If this carbon attacks this particular carbon, it will form 1, 2, 3, 4, 5, 6. 6-member ring is formed. So whenever you treat this OH minus, it will form a compound in this manner. C double bond OH. It will have C CH3, C CH3, C double bond O, CH2 minus. That will try to attack this particular carbon. C double bond electron and moves away, generating a compound in this manner. So intramolecular aldol is going to be possible only with respect to one compound. This O minus picks up proton from the water. It will form CHOH, CH2, C double bond O, CCH3, CCH3. And this has been heated also. Whenever you heat this, you will be forming a double bond which is in conjugation. Yes or no? Whenever you heat this, you will form a double bond which is in conjugation with C double bond O. This is in respect to major product. So what is a compound S? Compound S will be this final product. Compound R is a dicarbonyl, and this was your compound P and Q. Okay, this is your compound P. Right choice for P, because if you start with A, you are not getting intramolecular aldol. So after that, you will be getting compound P to Q. This is your compound Q. Compound Q upon ozonolysis, reductive ozonolysis, you get compound R. Compound R, you do the intramolecular aldol possibility, because 6-member ring is going to be formed. This is your compound S. Compound P, Q, R, S, got it or not? So we have to proceed with logical answers, logical approach. You cannot treat every option to be correct. Is that clear, students?
Yes, sir.
That's right. These are very interesting questions, like miscellaneous questions, since we are discussing the practice set. Try to solve next question. Next question will be like, in the following reaction, product S is the major product S is. This was a reaction set. Options also I'm writing here. I'll repeat this question. This is a reaction, compound given to you. O3 in the presence of H2O produces R reacted with NH3 produces. What is your compound? Yes, major product S. Okay. Find the major product S. Everyone try this question. Try this question for a minute, or understand the question what they were asking for a minute. Then we'll discuss. If you are done with the noting part, please let me know, students, so that I'll write the next question also.
Done, sir.
Suman, in which question? Like which double bond I'm not breaking?
Sir, in previous one,
Ozonolysis.
in benzene, yes, in benzene ozonolysis.
What they said, only dicarbonyl, no?
That's why.
Okay, that's why only. Okay. If I bake the double bonds of benzene also, I'll be getting a lot of other compounds which will never undergo intramolecular aldol. Okay.
Okay.
Okay. You try to solve that question. I'll be writing the next one, the next page. Let's look at this question, students. So 5-member ring, a 6-member ring connected with a 5-member ring. There was 6-member ring connected in this manner. CH3 group substituents, and a 5-member ring also present with a double bond here in this fashion. We are treating this with O3 in the presence of ZnH2O. O3 in the presence of ZnH2O, what type of ozonolysis is that? Reductive or oxidative?
Reductive.
Reductive ozonolysis. What I should generate in that case? What I should be generating in that case? I will be forming a respective dicarbonyl. Look at the options. From the options, you can see that the carbon-carbon double bonds of benzene are not broken. Only the C double bond C were broken. So CH3 you will get C double bond OH, CH2, CH2, C double bond OH. This is nothing but your respective compound R. This R treated with a NH3. The R is treated with NH3. What is going to happen now?
O minus NH4 plus will occur.
O minus NH4 plus will occur. After that, O
Sir,
minus
after
NH4.
that, no heating, amide formation will occur, but no heating is mentioned here, right?
So now why you are talking about amide formation? I am talking, is the reaction with respect to acid and NH3 or a carbonyl and NH3? Carbonyl and NH3, right?
Yes, sir, carbon.
Carbonyl and NH3 means we have to do amide formation, or you have to think of
Nucleophilic.
nucleophilic addition.
Nucleophilic addition.
Nucleophilic addition only. So what type? Like ammonia derivative. Reaction with respect to ammonia derivative we are going to have, right? Which is going to be attacked easily. Like again we have ammonia only. This ammonia we are having, again two carbonyls are there. This is a carbonyl A, this is a carbonyl B. Which carbonyl will be attacked by the lone pair of electrons on nitrogen? Because nucleophile has to attack
Carbonyl B.
carbonyl B because it is going to be aliphatic system. Aliphatic aldehydes are more reactive when compared to aromatic. So carbonyl B will be attacking because it is more electrophilic in nature. So what happens whenever you have the ammonia derivative? So NH2Z, you can treat this as NH2Z, or you can treat as this Z is hydrogen now. What will happen? This I can write as NH2H. The C double bond O, oxygen, and the two hydrogens from the nitrogen, they are going to be lost. Yes or no? What will happen is the oxygen from C double bond O and two hydrogens, they are going to be lost. Loss of H2 occurs. So I can directly write the product. You don't need to write the addition mechanism and all. Okay. With respect to ammonia derivative, what happens in the weakly acidic medium? So you will be having this reaction where you will be having the oxygen of C double bond O group and the two hydrogens from the nitrogen, they are going to be broken. You will generate the Amines system. CH2 single bond carbon, CH double bond NH. Because the Z group here is hydrogen, ammonia derivative or ammonia will react in this fashion. Now we have the system, right? CH2, CH double bond NH. This CH double bond NH and CH2 will that, what happens now? Think of this reaction. Again, we have C double bond OH, CH2, CH double bond NH. Can I write the respective tautomerase structure? If you try to write the respective tautomerase structure, I will be having this reaction. What reaction we are going to have is this hydrogen, this carbon hydrogen electron density that will come into this electron density moves away, and this nitrogen will pick up this proton. So like here you have C double bond O, that you can write as C double bond C OH or not. If I have CH2 CH double bond O, I'll write the respective tautomerase structure as CH double bond C CH double bond C OH. Yes or no? CH double bond CH OH. Like this you can write the tautomerase structure. The same tautomerase structure we are writing now to imine system. If you try to write the tautomerase structure to imine system, you will be having what? C double bond OH connected with a CH double bond CH, and you will have finally NH2. Finally, you will be having respect to NH2, and you have methyl group here. Now what will happen? The other C double bond O. Now we have other C double bond O. Again we have NH2. So intramolecular reaction is going to happen. The C double bond O group and two hydrogens, they are going to be reacting again. Yes or no, students? The C double bond group can be reacting with next set of ammonia derivative, C double bond H and NH2. This oxygen and 2 hydrogens are going to be lost. Again, loss of H2 occurs. You will be generating what? CH3. See, the carbon and nitrogen, they are going to be connected with double bond. CH obviously. And here you have CH, double bond CH, and these two are connected with nitrogen. This is your respective major product, which is equivalent to which is the right option. Okay. Which was the right option? Option A. Got it or not, all of you?
Yes, sir.
Yes, right. So these are tricky ones. These are not like straightforward questions. These are something tricky, so you have to be careful while answering. Try to solve this question. Benzene connected with CH2, CH2, CH2Br, and on the benzene also you have carbon bromine bond. That was stayed with set of reagents KOH aqueous CrO3H plus H2S for heating. Produces what type of compound? That will form what type of compound? All of you try to think on this question. Later the next question. An organic compound A, which has a molecular formula C9H10O, when treated with HI, undergoes cleavage to yield B and C. B gives yellow PPT with AgNO3, whereas C tautomerases to D. Whereas C tautomerases to D. D gives positive iodoform test. Positive iodoform test. A could be option A C6H5 OCH double bond CH CH3. Option B C6H5 CH2 OCH double bond CH3. Option C C6H5 O CH2 CH double bond CH3 double bond CH2. Option D CH3 CH4 OCH double bond CH2. An organic compound A, when treated with HI, undergoes cleavage to yield B and C. HI we are treating, and B gives yellow PPT with AgNO3, whereas C tautomerases to give D. So D gives positive iodoform test. So then the compound A could be what? That was the question. Okay. Previous question anyone solved? No one should feel disappointed, first of all, while looking at these questions. These are like interlinking question and miscellaneous questions. So if you're not getting answer, you have to try it only. Okay. Like we have a benzene ring connected to some two substituents. One is Br, other is CH2, CH2, CH2 Br. We are treating this with first KOH aqueous. What happens, students? KOH aqueous means
SN2 will occur.
SN2, because aqueous KOH, OH minus acts as a nucleophile. What type of alkyl halide? Primary alkyl halide. So SN2 will occur. OH minus will be attacking on that particular carbon where you have carbon bromine bond leaving group. So you'll have simply SN2 happening. Br, CH2, 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 OH. Stereochemistry we have not included, just OH is present. But of course, OH SN2 means inversion of configuration occurs, Walden inversion occurs. Now we are treating with the CrO3 in the presence of H plus. CrO3 in the presence of H plus. What type of compound this is?
Carboxylic acid will form.
Yeah, primary alcohols. Primary alcohol treated with chromic oxide in the acidic medium. CrO3 in the presence of H plus will be acting as a stronger oxidizing agent because it will lead to the formation of H2CrO4. This H2CrO4 has chromium in the +6 state. That chromium in the +6 state will be converting into chromium in the +3 state, and it will be acting as a stronger oxidizing agent. So we'll have the respective carboxylic acid formation. This carbon 1, 2, 3, third carbon will now connected with C double bond OH, and you have bromine here. So we have done first reaction, second reaction, we form the respective carboxylic acid, and third reaction is H2S4 upon heating. And can I say option C? I'll eliminate first, because the carbon bromine bond exhibits partial double bond character which cannot be broken. So in the option C we have COH, so that is broken, so that is not possible. So now this compound has to be treated with H2S4 upon heating. Carboxylic acid, we form a carboxylic acid, we are treating this with H2SO4. We are treating this with a H2SO4. CH2, 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 1, 2, 3, third carbon, C double bond OH. So this H2S4 will be producing H plus ions, which will attack the H plus ion from the carboxylic acid. Yes, Faizan given the answer. Faizan, which will attack the H plus ion from the carboxylic acid? Like two oxygens are there, oxygen A, oxygen B.
A.
Why? Why not B? B will attack, no, because lone pair of electrons present on oxygen A, they were in resonance with the C double bond of pi electron density. Yes or no?
Yes, sir.
So B will try to attack. So we will be getting this particular compound. C double bond O, oxygen will have only one lone pair, OH bond, and this carbon also has OH bond, and oxygen will have a positive charge, and we have bromine. Now what will happen after this step?
Pi electron density will move to oxygen, then benzene ring will attack carbon, electrophilic carbon.
Electrophilic carbon. The electrophilic substitution reaction occurs because the C double bond O with a positive charge on oxygen is more like this carbon is having more electrophilic nature. So C double bond O pi electron density will be moving away, and pi electron density will attack the carbon. So the pi electron density has to attack the carbon, and that is decided with this bromine or not. Bromine is electron donating group. Electron donating group will be ortho-para-directing group. For bromine, when you try to think of the position of the electrophile, that electrophile is going to be placed at the ortho and para positions, will be attacked at the ortho and para positions. Whereas the reactivity, if you try to compare, the bromine, even though it is ortho-para-directing, it is less reactive towards electrophilic substitution when compared to simple benzene. So ortho-para, this is ortho, this is ortho, this is para. So if you substitute the ortho position, you will be having more steric repulsions because there is no possibility of intramolecular hydrogen bonding. So para position is going to be attacking this particular carbon. This movement is going to happen. Now you'll have what? Now we'll have, I'll give numbering now. 1, 2, 3, 4, 5. 5-member ring is going to be formed. 5-member ring should be formed. And this carbon should be having this OH as well as other OH. This is the first carbon connected to second, second to third, third to fourth, third and fourth, no substitutions, fourth is connected to fifth. And which carbon should have a positive charge?
Second carbon.
Second carbon should be having a positive charge because it has seen the net loss in electron density. First carbon and fifth carbon should not be having any charges. And here we have hydrogen on the first carbon, which is going to be picked up by HSO4 minus. HSO4 minus will try to pick up this proton. CH electron density comes into, leading to the formation of this particular aromatic nature again. And we have a 5-member ring. And 2 OH groups on the same carbon unstable. So they will undergo loss of water to form. Dehydration is going to happen to form the respective carbonyl system. So we have carbon bromine bond. So we have C double bond O. This will be the respective major. So the electrophilic substitution is a tricky one. So that you have to find out from the reaction sequence. They will not be mentioning it anywhere. Right, students? Is everything clear so far?
Yes, sir.
Yes, right. Try to think on this question. An organic compound A, C9H10O, when treated with HI, undergoes cleavage to yield compound B. B and C. B gives yellow PPT with AgNO3. Something B is giving yellow PPT with AgNO3 means what conclusion I can derive? B is giving yellow PPT with AgNO3 means B should be releasing of the iodide ion because AgI is going to be formed, right? Whereas C tautomerase to D, C is undergoing tautomeration means C should be having enol system. D is giving positive iodoform means D should be having containing CH3 C double bond group. Compound A treated with the HI forming B and C. C should be having enol system. A should be having A is giving yellow PPT with AgNO3 means A is something which can release the iodide ion easily. So let us go with the conclusions. What they have mentioned is A treated with HI forms B plus C. B treated with AgNO3 forms LOPPT. LOPPT, that means AgI is formed. If AgI is formed, that means B should have a tendency to release. B should have a tendency to release I minus. C is undergoing tautomeration. C is undergoing tautomeration to form D. That means ketoenol form. Because based on the options given, only ketoenol form is possible. And D is undergoing iodoform means it should contain CH3 C double bond O group. So these are the points which you know from the question. So now we have to choose which is going to be the correct option among A, B, C, and D. Now let us go with the option 1. I have to choose one option only. So if I take option 1, I will be having respect to like HI, we are treating lone pair of electrons and oxygen, they will attack the proton, they will attack the H plus. So if I start with option 1, C6H5 connected to oxygen, oxygen lone pair is attacking the H plus to form OH, and you have what? CH double bond CH CH3, CH double bond CH CH3. Now which bond I can break? Which bond I can break? Can I break A bond? C6H5 is a phenyl group. With respect to phenyl group, the carbon oxygen exhibits partial double bond character. I cannot break this bond. So only possibility is I can break the bond B. If I can break the bond B, I'll generate what type of carbocation? If I break the bond B, I'll generate vinylic carbocation. Is the vinylic carbocation stable? It is not so stable. So I minus will attack in the SN2 manner or SN1 manner? SN2 manner only. So if I minus attack in the SN2 manner, you can generate this particular compound C6H5OH. Along with that, you will generate CH3, CH double bond, CHI. This is your CH double bond, CHI. So this is your compound, like this is your compound A. If I say this is your compound A, out of this, one should be B and one should be C. C should be undergoing ketoenol tautomerism. Will it undergo tautomerism? Will phenol will undergo tautomeration? No. Okay. No tautomeration due to aromatic nature. Because phenol is existing in the aromatic nature, right? It will not go into the keto form. So this C converting into D, that is not possible. So option A is wrong. And this is also not producing I minus ion. If it produces I minus, it forms a vinylic carbocation which is unstable. So B should have a tendency to release I minus. That is not happening in the option A. So option A is going to be wrong. Option B, go. Option B, C6H5 CH2 OCH double bond CH3. C6H5 CH2 OCH double bond CH2. First lone pair of electrons and oxygen attack the proton, so we get OH plus. Now I have to cleave the bonds. Which bonds I can cleave? I can cleave this bond or I can cleave this bond, A or B. Which can I can cleave? Which bond?
A.
B or A?
A.
If I cleave bond A, I will be generating a benzylic carbocation or not? I will be generating a benzylic carbocation which is more stable. So that is why whenever I am getting more stable than 3-degree carbocation, you have to go with the SN1 only. So SN1 occurs, bond cleavage happens. You will be generating CH2 double bond CH OH. And along with that, you get a carbocation like this. This is a benzylic carbocation that will be attacked by I minus now. So it will form what? CH2I. And this is your compound B, I can say. And this is a compound C. Compound C will undergo enol. So it forms CH3C double bond OH. This is a compound D. Compound D can undergo iodoform positive. So because it has CH3C double bond group, compound B will react with AgNO3 to form AgI because this carbon atom bond can be broken. So all the conditions are satisfied or not? When I
Yes, sir.
proceed with option B, I am getting B and C. C will undergo tautomerization to form D. D is undergoing positive iodoform because it has CH3C double bond O. B is undergoing I minus attack and we are getting C6H5CH2I which can treat with AgNO3 to form AgI. So all the conditions are satisfied. So only possibility is option B. If you go with option C or option D, you will not have follow at least one condition. So the right option is going to be option B because it satisfies all the conditions. Fine, students. So these are some miscellaneous questions and interesting questions which I want to discuss with you today. Okay, since this was a special class, people might not be knowing it, all the students. So we have our general session at 3:30. Okay, do join that class. Thank you all, everyone. Bye.
Thank you, sir.
Thank you.